Hi folks, our topic today is angular momentum. Just like all of our other angular quantities, angular momentum has a lot in common with linear momentum. So let's start there. What do you remember about linear momentum? Here are some things that probably come to mind. Momentum is always conserved. The equation for momentum is mass times velocity. Momentum is super helpful whenever we're talking about a problem that involves collisions. And there's this idea of impulse, where a force can change the amount of momentum that something has. Let's start with the equation. The equation for linear momentum is mass times velocity, and its units are kilograms meters per second. Angular momentum is going to have a very similar equation. The variable that we give for angular momentum is the capital letter L. Instead of mass, just like in rotational energy, we are going to use rotational inertia. And instead of linear velocity, we're going to use angular velocity. The units for angular momentum are kilograms meters squared per second. Notice that those are different units than momentum. That means that momentum and linear momentum are separate quantities. Unlike rotational kinetic energy, where that's just another form of energy to add to our mix, momentum and angular momentum are separate things that need to be treated separately. But both of them are conserved. So let's review what we mean by the conservation of linear momentum. What we mean is that if the net force on a system is zero, the total momentum of that system stays constant. If we write that as an equation, it looks like this. If net force equals zero, the sum of the momentum before the event is equal to the sum of the momentum after the event. Angular momentum is pretty similar, only instead of force, we're going to use torque. We could write it out in words this way. If the net torque on a system is zero, then the total angular momentum will remain constant. And writing it in equation form looks like this. If net torque equals zero, then the sum of the initial angular momentum equals the sum of the final angular momentum. We will talk about 3 different applications of this idea. We will talk about single spinning objects, gyroscopes, and collisions that cause rotation. When we consider a single spinning object, what we mean by the conservation of angular momentum is that the object's inertia multiplied by its rotational velocity will be the same at every point in time. This becomes interesting because an object's inertia depends on its dimensions. My favorite example of this is a toy called a Hoberman sphere. The sphere starts off with a large size, but if you compress it, it will collapse into a very small volume. In which of these cases is the inertia larger? Well, when most of the mass is far from the axis of rotation, the inertia is larger. So the sphere has a much larger inertia when it's expanded and a smaller inertia when it's collapsed. How will that affect its behavior when it is spinning? Watch as the man collapses the sphere. It spins much faster. Why? When the sphere is large, it has a large rotational inertia, which means it will have a small angular velocity. When you collapse the sphere, the inertia becomes small, which means to equal the same value, the rotational velocity must be much larger. The same phenomena applies in figure skating and gymnastics and gives the beauty to these sports. An athlete can change her inertia by expanding or contracting. When her arms are out, she has a large inertia, and when she pulls her arms in, her inertia is much smaller. Watch as the skater spins below. As she pulls her arms inwards, her inertia gets smaller, which means her angular velocity increases. Angular velocity also governs the universe on the large scale. Think about how stars form. They form when large, dusty regions called nebulas start to collapse under the force of gravity. As the mass moves inwards and the dust collapse, the radius of the system decreases. That means that the inertia of the system also decreases. By the conservation of angular momentum, this means that the rotational velocity must increase in order to balance the decreasing inertia. As the angular velocity increases, the entire system spins. This is why solar systems all spin in the same direction, and this is why some collapsing stars start to spin at amazingly fast speeds. When is the last time you played with a fidget spinner? What are some things you remember about how it felt? Did you notice that it's difficult to turn it over once it's spinning? Or that it tends to balance better when it's spinning faster? A fidget spinner is similar to a gyroscope in those respects. Both are great examples of how the direction of angular momentum is also conserved. Momentum and angular momentum are both vectors. That means they have an amount and they have a direction. So, how do we determine the direction of angular momentum? It's a little bit tricky since the entire object is spinning in many different directions all at the same time. In order to find the direction of the angular momentum, we use a trick called the right-hand rule. With the right-hand rule, you use your right hand. Your fingers wrap in the direction that something is spinning, which leaves your thumb pointing in the direction of the angular momentum. Let's try these with a few examples. As this top spins, what direction is its angular momentum? Take a second, wrap the fingers of your right hand in the direction of the spin. Your thumb should be pointing upwards. That means that the angular momentum in this case is directed upwards. What about here? As the man with the leaf blower spins in his chair, wrap your fingers around in the direction that he is spinning. Notice your thumb is pointing down. That means that the angular momentum in this case is pointed down. What about the gymnast? As he spins, wrap your fingers in the direction of the spin, and you should notice your thumb is pointing to the left in the direction of the bar. When we say angular momentum is conserved, we mean that its amount and its direction are both conserved. This is why a gyroscope works. As it spins, it has a particular direction for its angular momentum. Consider the gyroscope below. As it spins, its angular momentum is directed upwards. Just like it would take a force to change the momentum of your car, it will take a force to change the angular momentum of the gyroscope. That means a force is required to tip it over.